Good morning and welcome to another LEAP seminar. Today we have the pleasure to have as a speaker Elias Asamar. Elias did his PhD on LHCb experiment at the University of Barcelona, and after that he worked in the experiment of super CDMS, staying in several places, namely Madrid, Durham, and Minnesota in the US. He joined LEAP at the beginning of last year to work on the LZ experiment and on the Migdal experiment, which he will present us today. Thanks, Elias, for being here, and you may start whenever you want.
All right, thank you very much. So the subject of this seminar is the search for dark matter particles using xenon detectors. I will go through all these points. I will start introducing dark matter and then progressively going to the detection, double phase detectors, and I will focus on one experiment, which is LZ. And then after that, I will move to another related subject, which is the confirmation of the Migdal effect using the Migdal experiment. And then I will talk briefly about the future prospects for xenon experiments. So to start with, dark matter is one concept in astrophysics and cosmology, which is necessary to explain a series of effects, gravitational effects that are observed. So we observe this effect, but we don't see any matter causing that. So what is hypothesized is that there exists this dark matter that is causing those effects. This dark matter component is actually more abundant in mass than ordinary matter and accounts for approximately 80% of the total mass of the universe. These effects are, as I said, this is quite consolidated. These effects are observed over a wide range of scales, from galaxies to cluster of galaxies to the entire universe. And so it's a consolidated concept in astronomy and astrophysics. So we know we are very confident that it exists, but we don't know what this dark matter is made of. In order to agree with observations, this dark matter needs to satisfy three requirements, which are written here. One is that it should be electrically neutral. Otherwise, we would have observed it in some way in the electromagnetic spectrum, but we see, as I said, we see nothing. So this is one requirement. It should be stable because it's there since the beginning of the universe. And according to how it's distributed, it should be non-relativistic. Or in other words, it should be cold. So dark matter must satisfy these three requirements. And the problem for particle physics is in the current standard model of particles, there is no particle that could account or could explain this dark matter. So we postulate that dark matter is made of a new kind of elementary particles. So we see here how a concept that is originally from astrophysics and cosmology has implications, deep implications in particle physics. The three requirements that I mentioned before in the previous slide are basically the only constraints that we have on dark matter. Other particles, on dark matter particles, other properties are unconstrained, and in particular the mass of dark matter particles. So it can have any mass. We see here a spectrum of candidates that go to the very light QC reaction to primordial black holes, and anything in between could be a candidate. So there is no constraint on the mass. And for this reason, there is a lot of models that are trying to explain, but we don't know which one is true. Among these models, one interesting or very popular one has been the weakly integrating massive particle hypothesis. That has been of interest because without needing to add any other interaction in the standard model, it can account naturally for the observed amount of dark matter in the universe. So in this case, the only additional ingredient would be the dark matter particle, but we don't need an additional interaction. In this case, the dark matter particles interact with ordinary matter, have some coupling to ordinary matter through the standard model weak interaction. So, and the natural range of masses is in the GeV scale. This is shown in the spectrum above in a square. Then there are more general dark matter models that explain the observed amount that are more general, but can have other interactions different, or new interactions different than the standard model with interaction. These models include hidden sector, asymmetric dark matter, and fleeting dark matter. And in this case, because these models are more general, include, and you can see, as you can see in the plot also, dark matter that extends below the GeV regime. And this, we are referring to that to sub-GeV candidates. Here now I'm going to explain about ways of trying to detect these dark matter particles, and I will focus later on one of them. So there are three domains, basically. One is according to how we arrange this interaction between ordinary matter and dark matter, we have three ways, three domains. One is the domain of colliders, where we produce dark matter particles from standard model ones, and this can be explored at colliders. Then we have indirect searches, where that's in the domain of astronomical observations, where we look for products of dark matter annihilation. So it's the opposite of dark matter creation, and we look for that in regions of high density, where we expect to have high density of dark matter. And the latest one, the latest point, is in the domain of low background experiment, which is a direct searches, and this is what I'm going to focus on now. So the idea of direct WIMP searches is that because dark matter is distributed all over our galaxy, we should have some dark matter population around the Earth, in the Earth vicinity. So the idea of direct detection is to detect this galactic dark matter by placing a detector and seeing interactions of that. So this is what is written here. We aim to detect an excess of recoiling particles, atomic nuclei or atomic electrons. This is our signal in a given volume, which is a target caused by this interaction with our galactic WIMPs. And note that in this case, the target, where we expect to have interactions between WIMPs and ordinary matter, should also have the ability to detect the recoiling particles. So you produce, as is shown here, you have dark matter interacts with a nucleus, for example, that it recoils, and then the volume itself that is acting as a target should detect this recoiling nucleus. So an experiment like this should be target and detector at the same time. Just to see what are the energies involved here, an assumption is that dark matter has of the order of 200 kilometers per second velocity. If we assume a WIMP, it's of the order of GeV, and with those assumptions, the expected recoil energy for a nucleus is of the order of 10 keV of the keV scale. The interaction can produce can be with an electron or with a nucleus. In our case, if we are considering WIMPs, because of the mass and the expected velocity, the optimal energy transfer occurs when the mass of the target, of either the nucleus or the electron, is of the same order of magnitude as the mass of the dark matter particle. And because we expect dark matter particles, in this case for WIMPs, of the order of 1 GeV, we focus on nuclear recoils, because we expect the process to be more efficient in terms of the recoiling particle have more energy. At this point, I want to explain a bit what's the information that we can extract from that recoiling particle. So if we assume that we know, and we have some reasons to assume that, to make those assumptions, we assume the density of dark matter particles of WIMPs at the earth position, and also the velocity distribution of those particles, then the signal, the recoiling nucleus that we want to observe depends only on the mass of the WIMP and the coupling that has between the dark matter, the WIMPs, and the nucleus. I'm going to explain that a bit more in this plot. So this is a plot of the expected energy spectrum of a recoiling nucleus, in this case in a germanium target. So this is the energy that would have a germanium nucleus for different WIMP masses. And we see that the energy spectrum, red is the lightest one, and then increasing in mass. And we see that the spectrum is softer for a lower mass, and as the mass increases, the spectrum gets a bit harder. So whether the energy spectrum is harder or weaker, that gives information of the mass of the dark matter particle. And the coupling just has implication in the normalization. If you have a stronger coupling, you will have more events, and then the normalization will be larger. So the normalization gives you the strength between dark matter and ordinary matter. In general, we have limits on these quantities. So the limit on the mass is the limit on the energy threshold. So because lower dark matter particles give weaker or softer spectrum, the energy threshold gives a limit on the mass. And the target mass, the exposure time, and the background levels that gives you the quantity of events that you can see sets limits on the coupling. Because the background is important in these cases, because we want to observe rare events, we need to address and try to suppress as much as possible the background. In this case, because of the energies involved in the processes, which we expect, as I said, recoiling nuclei in the KV regime, we must reject processes in the domain of those energies which are caused by environmental radiation, natural radioactivity, and cosmic rays. For this reason, we use underground facilities to carry out our experiments. We build shielding around our experiment, and we use our experiments or our detectors with radiopure materials in order to suppress as much as possible these backgrounds. And with respect to the techniques to observe the nuclear recoils, one important fact is that although we have this background rejection techniques, we still have a large background of recoiling electrons in our experiments. So we want to look for nuclear recoils, but we have this background of recoiling electrons that can be caused by gammas, beta decays in the bulk, and a series of processes. So it is good if we can discriminate between these two kinds of recoil. We're going to have some particle identification. And to that purpose, what several experiments do is to measure two effects that the recoiling particle causes in order to distinguish these two particles. One approach carried out by solid-state detectors is to measure ionization produced by the recoiling particle and also phonons. Phonons is quantized vibration of the lattice because they are solids, and measuring that and measuring the two quantities, you can have some discrimination between the two recoiling particles. And another approach is using scintillation and ionization in novel elements, as I'm going to explain now. So now I'm going to focus on that part, on dark matter experiments using novel elements, in particular xenon, and in particular double phase detectors. Why double phase detectors? I'm going to explain here what's the mechanism here. So the parts or the components that are necessary in these detectors are the following. So first we have a target, large target, as large as we can, of liquid xenon. It's what is shown here. So that's our target, and that's liquid. And on top we have a layer of gaseous xenon. So this is why it's double phase detector. We have these two parts. Then we have an electric field, which is downwards, that would drift electrons upwards from the target of liquid to the gaseous part. And that's achieved by these grids here that are shown. So we have a cathode at the bottom and another at the top. And in between, in the interface between the solid and the gas, another grid. The function of this grid is to create an electric field with a given strength in the liquid and a stronger one in the gas. But besides that, it's a vertical electric field. And in addition to that, a series of light detectors. So we want to detect light in this volume, and we have an array of PMTs on the top and at the bottom. And what happens in these detectors? So first, imagine that we have, in our case, a WIMP that interacts with a nucleus and makes it recoil in the target, in the liquid target. So that particle that is recoiling produces two signals, one scintillation and ionization. And that the amount of scintillation and ionization that are produced in the recoil depends on the recoiling particle. So an electron will produce more ionization than scintillation, and the other way around for a nucleus. The scintillation that's light, that's in the ultraviolet regime, and that's promptly detected by the PMTs. So this is what we call S1, is just the scintillation, detected almost instantly. Then we have the ionization that drifts because of the electric field and enters the gaseous region. And then in the gaseous region, it produces proportional light, proportional to the amount of ionization, by a process called electroluminescence. And then with some delay given by the drift time of the electrons, there is a secondary signal produced by this electroluminescence, which is called S2. So the signal that we have is the prompt scintillation followed by the proportional signal after a delay time, which is a drift time. And these are the two signals that allows us, first of all, to see the recoil and then to discriminate it. And there is several pieces of information that we can extract here. So one is because the drift time depends on the depth. The more depth, the more drift time. By measuring the drift time between S1 and S2 allows us a precise measurement of the vertical position of the interaction. So we have position information vertical, in the vertical direction. Also, because the ionization and the scintillation, the relative amounts depend on the recoiling particle. By comparing S2 to S1, we have discrimination. We can discriminate nuclear recoils from electron recoils as we wanted. And we can see that in this plot here. So this is LUX data, and we can see here two bands. In the x-axis, this is the S1 signal, so the scintillation signal, and in the vertical axis is the ratio between S1 and S2. And in this space, we have two populations. The top band, which is the events where with more S2 compared to S1. These are electron recoils, and we see that our background is populated by electron recoils, as we would expect. And then we have a band corresponding, that we obtain that with calibration data, corresponding to nuclear recoils. And we see here that it's emptier. It's basically leaking from the electron recoil band, events that leak extend towards the nuclear recoil, and those are events with suppressed S2. And we see here that we can discriminate between these two populations. This is important to reject and to have a signal region that is cleaner, that is not contaminated by the majority of electron recoils. And in addition, I mentioned that we have some vertical information position, but because we have an array of PMTs, we also have some radial position. By looking at what PMTs fire and how the energy distributes, the light distributes over the PMTs, we have also radial position information. So summarizing, with our dual phase xenon TPC, we can detect recoiling nucleus down to 3 keV approximately, then have electron recoil, nuclear recoil discrimination, and also have position information. With these devices, we have obtained the best WIMP sensitivities to date. These are the results so far, and these are the best among the direct WIMP searches. This is same as I showed before. So on the x-axis is the WIMP mass, on the y-axis is the coupling to ordinary matter, and what is excluded is what is above this. What is below cannot be excluded because we have not taken data for more time and because we start to observe some background, so we cannot exclude more rare events. And on the horizontal scale, we cannot go lower because of the energy threshold of our detectors. So, and we exclude the top part. And in addition, I would like to finish this part mentioning this excess that has been recently recorded by Xenon 1 ton. So this is not affecting our WIMP searches because WIMP searches are using nuclear recoils, and this is an excess of recoiling electrons. So this is not observing more recoiling, this is observing more recoiling electrons. And this is below the 5 keV. So it's a different signal, and there has been, so you can see the excess here at low energy. So this is the energy spectrum. You have your expected background in red, and the data are the black bars. And you see this excess, which is near the threshold, is I think 3.5 sigma or something like that. And there are two kinds of explanations, one that involves new physics, as solar actions or enhanced neutrino magnetic moment, although these hypotheses are highly constrained by astrophysics reasons, or some kind of unaccounted background. The collaboration, Xenon 1 ton collaboration, is mentioning tritium as a possibility, but it's true that also argon-37 has a X-ray line at precisely that energy. So far, we don't know what it is, and that's something that to definitely keep an eye on. Now, at this point, I'm going to focus on one experiment using double phase xenon TPC, which is Lux Zeppelin. This experiment is a second generation experiment as a continuation of Lux and Zeppelin experiments. As an evolution of these experiments. This proved to provide very good results, and merging, we are producing this new experiment, more sensitive experiment. The purpose of this experiment is to explore even weaker couplings that are not yet excluded of WIMP. So we want to explore signal with smaller rates than before. This is important to understand the experiment. So we want an experiment that is sensitive to slower or lower rate signals. The status of the experiment currently is ending its construction. Actually, the experiment, the detector itself is constructed. It's just part of the shielding that remains to be assembled. And we plan right now to start science data taking in late spring next year. I'm going to explain here the details of some details of the experiment. The size of the TPC, which is the volume here that I'm now showing, is approximately 1.5 meters, both in height and in diameter. And this volume contains 7 tons of liquid xenon. However, not all of them is being used for searching for that matter. We define, using the position information, we define a fiducial volume in order to reject surface backgrounds, and we keep the central region. This is viewed by an array of PMTs at the top and at the bottom, as I mentioned before. And what happens here is, as I explained, in the target, we produce the scintillation, then the ionization produced by the recoil is driven upwards, and we can see in the zoom image what would happen. So the ionization would be coming from the bottom, from the target, from the bulk of the experiment to the surface. And in this region here, the surface of the liquid is at the top of these small white blocks shown here, where the gate grid is, and then it's extracted from the liquid into the gaseous phase, which is here. And in this small or thin part here is where the electroluminescence happens, and then is detected the S2 at the with the top array PMTs, and also in the bottom if it's strong enough. So this is regarding the TPC. The TPC is inside a cryostat which has 2 layers. It's made of titanium. This is the outer layer that contains the inner layer that contains the xenon, and then the outer layer, which is this, and it's made of titanium, as I said, ultra pure titanium. One important component of the experiment is the shielding, and the reason for that is because, as I mentioned before, we want to observe events or signal that occur at a smaller rate than before. So we need to achieve better background rejection, background suppression than the previous experiments. If we stay the same, then we will not be able to have the required sensitivity. And the approach that LZ has followed to reject the background of electron recoil, the background, part of the background is to use an active shielding, as we can see here. And I'm going to explain a bit how is the concept, the principle of operation. We have here at the center the TPC, as you can see, and the cryostat in green. And then we have a material that is instrumented, and we can see interactions occurring there. So we have first what we call a xenon skin. So it's xenon outside the TPC. So in this zoom part here, we see the TPC here and some xenon around it, which is not inside the TPC, but it's also active. So we can see interactions here. And beyond the cryostat, we have the outer detector, which is also sensitive. And even beyond that, we have a water tank that is to provide further shielding. And as you can see, the xenon skin is instrumented with some PMTs at the top and here also at the bottom. So we can see something, interaction happening there. And with this outer detector PMTs, we can also see scintillation in the outer detector. So the idea of this is, because backgrounds, in particular neutrons, and also some gammas, will interact more than once. If we see an interaction in the TPC, but also outside, we can recall that event, right? So we will have some radiation entering the TPC, but if we are able to detect activity also on the outside, in coincidence with that in the TPC, we can we will with confidence, we will be able with confidence to say that that's a background and to reject that. And note that we will have just a passive background, we will not be able to do that. So that's the point of using an active shield. So on one side it shields, but on the other side it detects backgrounds. So that's the point of having active shielding. With the expected background that we expect to have is shown here. We expect to have a total of 6.5 background events passing the WIMP source selection. In the spectrum shown here is the on the left is that from the electron recoils, and on the right from nuclear recoils. As you can see, the background from nuclear recoils that is caused mostly by neutrons and neutrinos is lower than electron recoils, but the electron recoils, this is before discrimination. So once we discriminate, that decreases a lot. The most important contribution, as you can see here also, is radon dispersed in the xenon itself. That's providing, out of these 6.5 background events, it's providing approximately 4 events, so that's dominant. And recoiling nuclei, that basically only 0.5 events. So that the dominant is this electron recoil background that remains after applying nuclear recoil electron recoil discrimination. At this point, I would like to add this work that has been done here at LIP this year as a summer internship, which is the estimation of the background from argon-37 and tritium, assuming the same contamination levels that would explain the xenon quantum excess. So, as I mentioned earlier, one of the explanations of that excess could be that there is some unaccounted background. That background from tritium or argon-37 has not been accounted in the LG background model because we consider that to be negligible, have not a big impact. So that has not been considered. But after seeing the results, we have proposed this study as a summer internship, and our student did this work that is shown here. So basically what he did is to calculate the spectrum and add it to the already expected background, which is this flat line here, and flat line also in the left, and normalize the additional contribution to the contamination level that would explain the xenon quantum excess. And you can see here what you expect to see in terms of events. So that's normalized to what you would expect with those rates. And in particular, it's important to note that the argon contribution would be precisely at the position where the xenon quantum excess is. With these background estimates, we expect to obtain the sensitivity shown here to WIMPs. The curves shown here are the existing limits. It's not shown here the latest xenon quantum result that would, the minimum would be like here, but still LZ would provide a more than 1 order of magnitude improvement with respect to the existing limits, as you can see here. And that would represent an important step towards approaching the neutrino limit. If in case that you are wondering what this neutrino limit is, this is just the rate at which we start to observe background from coherent neutrino scattering. We have not, we will not be reaching that limit. We still not have sensitivity to that, but using this in this part, but it's a limit that it's expected to be there, and at some point, experiments are expected to hit that. In addition to this standard dark matter WIMP search, there is several other complementary dark matter searches that are planned that I'm briefly mentioning here. One is the WIMP search below the nominal threshold. The nominal threshold is set because we want, as a requirement, to observe both S1 and S2, but the threshold on S1 is higher than S2. So if we use the S2 signal only, we are losing electron recoil, nuclear recoil discrimination because we only have one signal, but we can lower the threshold because the threshold on S2 is lower. So this is one way of going to lower energies. Your limits will not be as good as if you use the discrimination, but you will be able to go to lower energies. Another important analysis that can be done is sub-GeV dark matter particles. In this case, you can go even at lower thresholds using this effect, but I'm going to talk about this in a while. And then we can do searches using the electron recoil spectrum. One word about actions. We don't have sensitivity to dark matter actions, but we can study solar actions with our detectors. And in addition to dark matter searches, LZ will be able also to do some neutrino and nuclear physics studies because of its large mass and its low background levels. I'm listing, just want to mention here, some of the analysis that can be done. We could be able to observe coherent scattering of boron-8 on nuclei, study neutrino magnetic moment, and also several rare decay processes, both in the realm of nuclear physics, like double beta decays, as xenon 134, or electron capture positron emission of xenon 134, or searches for neutrinos double beta decays. We have here the sensitivity on the right for neutrinos double beta decay of xenon 136. You can see that after a lifetime of 1,000 days, we can achieve sensitivity comparable to that of condensate. And on the right, this is for the two neutrinos, so for an allowed process in the standard model, two neutrino double beta decay of xenon 134. These lines, these straight lines, are predictions, and this is the expected sensitivity, and we might get there after again 1,000 life days. Having explained the LZ experiment, I'm going now to talk a bit about the Migdal effect and the experiment that is done to try to confirm it. What is this effect and why it's so important now? This effect has been proposed quite some time ago, and it's basically an ionization mechanism that works as follows. So it's ionization of an atom caused by a perturbation in the nucleus. Okay? So, and the idea is, this is depicted here. So whatever, for whatever reason, in this case, because of that matter particle, the nucleus gets disturbed, perturbed, then that perturbation causes, that also affects the electron cloud, causes ionization, and then we have the recoiling nucleus on one side and the electron on the other, which is detached. And the idea behind it is that for the moving nucleus, the eigenstates, which are shown here, of the moving nucleus are not orthogonal to those of the nucleus at rest. So then you have some transition probability, non-zero transition probability, between ground and ionized electron states. and that's because of that. And then more recently, there has been this study to check the energy and momentum conservation of this effect in the context of dark matter searches. As I said, this is for a perturbation of the nucleus, which can be from a dark matter or any other particle that perturbs the nucleus. And this effect has been discussed theoretically, but there is no experimental confirmation of this. However, several experiments have used it to extract limits, because you have, it's a different signal. You don't have only the recoiling electron, you have the, the recoiling nucleus, you have also a recoiling electron. And there has been studies for that, and you can see here that you can achieve a quite low threshold even in xenon experiments. So you can see that this is the explosion plot, as I showed before. In the horizontal axis is the dark matter particle mass, and you can see the limit here of lags xenon 1 ton at few GeV here, not going beyond for this kind of experiments. But then using Migdal effect, you see these lines. This is for lags, so you can see the improvement. You can improve your mass by almost your mass limit by 1 order of magnitude approximately. So this is quite an important effect. So with this effect, you are opening the door for xenon experiments to be also competitive to search for sub-GeV dark matter particles, not only for WIMPs. And you can see the reason here on the left. For a 2 GeV dark matter particle, you see here, this is the energy spectrum. You see the energy spectrum of for pure elastic scattering dark matter with a nucleus, and you see a threshold below the keV scale. But using the Migdal effect, this is the energy spectrum of the Migdal electron, and you can see that it goes above the keV approximately threshold. So this can be observable even though the nuclear recoil is not observable. So this opens new possibilities, very interesting possibilities for xenon experiments. As I said, this is not confirmed yet. So one team from British and also from LIP and from CERN researchers, we are trying to confirm this effect as follows. We plan to induce Migdal effect in a tracking detector using neutrons. So the idea is to not induce the Migdal effect with a perturbation in the nucleus caused by a neutron, and then observe the recoiling nucleus and the Migdal electron, so 2 tracks with a tracking detector. And the signal here is a recoiling nucleus and an electron of approximately 10 keV. This is the energy of the Migdal electron with the same vertex using a tracking detector. And in this case, the Migdal effect would be caused not by dark matter, but by a neutron. Okay, this is our way of controlling or inducing the Migdal effect. To have more details, the neutron source in this case is a deuterium generator, which 14 MeV neutrons at a quite high rate. So also the interest of having this source is the high rate of 10 to the 10 neutrons per second. The target gas is CF4. The reason for that is that it scintillates, and so we want that to have an image of the track. And in order to be able to have a visible Migdal electron track, we need low pressure. So this gas is at quite high, quite low pressure. Okay. And if we assume this active volume of 10 times 10 times 5 centimeters, cubic centimeters, the predicted signal rate of Migdal events is 200 Migdal events per day. This is shown here, how the rate decreases with the threshold energy. So if we have a threshold energy of 5 keV that we think that we can have, it's approximately 200 Migdal events per day, which is quite good. Now explaining the tracking device itself. So I have explained what gas we are going to use, what neutrons to induce a Migdal effect. Now, how we are going to observe these two tracks, this nuclear recoil and this electron track. So we are going to use an optical TPC, which consists of a cathode and an indium tin oxide anode. I'm going to explain why this type of anode. Then between the anode and the cathode and the anode, there are two GEMs that provide amplification of the ionization. In case that you are not familiar with GEMs, they are just thin foils with holes in it where electrons go from one side and then get accelerated and amplified at the holes as is shown here. So in this case, one ionization comes from one side to the hole and then gets amplified, and at the exit, you see an amplified electron, multiplied electron signal. And then a camera that is going to capture a scintillation. And this is the sketch of the TPC that we are going to use, and I'm going to explain here. I'm showing here how it looks like in reality. So we have our camera, our container here, and this is without the flange, so we can see inside. We have a cathode. The active region is the region between the cathode and the two GEMs. We want to fire our neutron beam here and produce Migdal events right here where I'm signaling now, and produce ionization there. And this is the principle of operation of the optical TPC. So as I said, with the active region is within the cathode and the GEM. We fire our neutrons here. We produce Migdal, we expect to produce Migdal events in this active volume. Then the two tracks will produce charge, ionization, that will drift because of the electric field to the GEMs, go through the holes, get multiplied, and because there is CF4 scintillating gas, this multiplied electron signal will produce light mainly at the holes. This light will be captured by the camera, and it's important to know that this light will follow on the GEM the pattern of the 2D projection of the track. So we will have an image of the 2D projection of the tracks in the camera. So this is already 2D information. And then this amplified signal will go, charge signal will go to the ITO anode and be collected as electric current. And the timing of this current will provide information of the depth of the interaction position. One reason to have ITO anode is that it's transparent, so we can see through it the light that is produced. So we can collect charge in the anode while being transparent to the light, scintillation light. And with that, the image that we plan to see is like this in the camera, so in the scintillation light. So one strong signal from a recoiling nucleus, and then a Migdal electron track that goes on the other, that forms a vertex with a, you can see here the vertex. And we plan to be able to identify that and tag that as a Migdal event. One important component, again, in this experiment is the shielding and the collimator. The reason for that is because the source is isotrope, the neutron source is isotrope, but we only want neutrons in one specific spot, as I showed. So we need to reject anything else. And LEAP Coimbra has had an important involvement there, optimizing this front shield. So the optimized design of sizes of this shield, and in particular of the collimator, has been determined here on basis of Monte Carlo simulation. One important concept is this, or part is this collimator, which is shown to be very sensitive on the design. We initially used this collimator with this shape, with a single trapezoid, but then we found, and that we found that this shape, this double trapezoid, it allows for better suppression of the background. The background that we expect, just to remind, the signal is 200 events per day. The background is approximately 30 events per day. And they are mostly caused, and we also find that here, by random coincidence of two tracks, of a nuclear recoil produced by a neutron plus an electron caused by a gamma, for instance, but independent. So if we found no other relevant background, that should be good, and that would allow us to observe the Migdal effect in case it exists. And approximately we plan to take 1 month of data taking. And now we are starting construction, and we plan to operate before the end of the next year at some point. And in case of being successful and confirming the Migdal effect, we plan to also include argon in the mixture and xenon, and study Migdal effect in noble gases, which is the purpose, because we want to study Migdal effect and to have Migdal effect in xenon detectors and in a lower energy regime, because we are interested in that regime, in having sensitivity to low recoils. And now, before ending, I'm going to comment on the future prospects for xenon experiments. We are confident that this technology, the dual phase xenon detector technology, has the potential to continue leading, providing leading results in this field after G2, after LG. And because of that, there are R&D proposed in order to try to achieve these two objectives. One is to be more sensitive to weaker coupling of matter and ordinary matter. And we think that here, again, xenon detectors will continue leading this field. And we also have now handles to observe or to search for sub-GeV matter. So we also want to exploit that. And using or considering these two objectives, there is these R&D activities that are proposed. There are more, but I think these are the main. One is, instead of using PMTs to detect light, is to try to see whether using silicon photon multipliers could improve the detection of S1 and S2. Also, I mentioned that the main background contributing with 4 events to the 6.5 background events in LZ is radon. So there is planned R&D to try to improve radon removal from liquid xenon that would allow us to remove the most important background for LZ and go to sensitivity to weaker processes. Confirm the Migdal effect, which I have discussed, and also going towards the detection of sub-GeV matter, study the feasibility of using xenon detectors doped with hydrogen for using for searching for low energy, low mass matter. The idea of this is to have xenon detector with some quantity of hydrogen gas in it. So in this case, because the hydrogen has a lighter mass, it would receive more energy from the dark matter particle and leave more energy in the detector. So from the kinematics point of view, it's more convenient hydrogen than xenon. But on the other hand, xenon has as you can see here, a lower ionization energy, and we know very well and has very good detection properties. So the idea is to use the hydrogen gas diluted as a target, and then the liquid xenon as the detector medium. Yeah, right. And that's why this doping, this mixture of these two elements. And in fact, this is the sensitivity. So this, again, this is R&D. So this is just studies ongoing. And we can see here the sensitivity. So again, the horizontal axis is a mass of that matter. We can see here limits of conventional searches at 5 GeV, GeV. But we can see that using xenon detector doped with hydrogen gas, we can improve by almost 2 orders of magnitude that. So it's quite an important improvement. So we want to investigate that. And with this, now I close that. I finish the presentation, the seminar, just reviewing the most important concepts of it. First of all, that double phase xenon TPCs with a liquid phase and a gaseous phase measured to signal a prompt scintillation, and then electroluminescence light from ionization producing the gas. That's why we have 2 phases. This allows us to have electron nuclear recoil discrimination. Xenon experiments with this technology have achieved the best WIMP sensitivity today, and there are plans for operating a new machine, which is xeV, which is a second generation experiment, so taking advantage of a previous xenon experiments that will extend the search for WIMP programs. Besides that, we have the opportunity of also studying sub-GeV dark matter in xenon detectors if Migdal effect is confirmed. And to that purpose, there is an experiment which is called Migdal, trying to confirm this effect by inducing it with neutrons and using a testing detector. And finally, that there is still room where double phase xenon TPC technology can continue leading dark matter searches after else. And that's everything. I hope that you enjoyed that. Thank you for your attention.
Thank you very much, Elias, for this very nice and very interesting presentation. We have now some time for questions. Please raise your hand or just speak up. Noon, please go ahead.
Yes. Hi, Elias. I mean, I think you might have answered the question that I'm going to ask, but in that case, I'll ask you to try to summarize. Can you hear me? Otherwise?
Yes.
Yeah. So basically, you presented the sensitivity for LZ. I mean, and you showed that it will have more than order of magnitude improvement with respect to current limits. And then you said that you're approaching the Neutrino 4. And then in the end, you presented some prospects. And my question is, I mean, what would be the main strategies to advance into the Neutrino 4 to push the limits for sensitivities below the Neutrino 4?
I couldn't hear very well the last part. Is your question whether we can reach the Neutrino 4 with generation 3? Or
yes, I mean, so what ways are people exploring to try to still have sensitivity despite achieving the rates for the neutrinos? I mean, so what are people trying to do?
Well, I mean, this is still very in the initial steps, but one important step to reach there is to again lower the background rates. The most important is to remove them. What would be now the main contribution, which is radon. I think that the focus is here, and the plan is to reach with this third generation experiment to reach the Neutrino floor. And I think again the first step is this, and then I'm not aware of other other background rejection R&D, but this is definitely the most important one.
Okay,
And
thank you.
then,
Yeah.
and then if we want to move beyond the neutrino floor, then if we want to reject have some background discrimination, there are options which are directionality, because we expect some directionality from the neutron, from the background. But then that's there is R&D, but on a different detector technology to achieve directionality. Not completely right now. But that's beyond the neutrino floor. I think that for reaching the neutrino floor, xenon is the best technology.
Okay.
Thank you. Thank you. Good to know.
Yeah.
So next it's Sophia.
Hello, morning. So it's very interesting, this Migdal effect. Though I want a little bit more detail on I didn't get totally the energy scales that we are talking about, and if it depends, how it depends on the mass of the nucleus, etc.
Yes.
Because your experiment, you will do it with carbon and fluor, right? But then you want to go to the noble gases that are heavier. Do you expect a big effect there?
Yes, and also, so you have in terms of threshold, you expect to have a lower threshold for lighter nucleus. The plan of so the initial plan was to use argon and CF4, but we found that if we want to first confirm the Migdal effect, it's easier to just have CF4. So this is just for practical reasons, and we expect a slightly lower or higher threshold for argon and xenon, but again, the purpose of this is a first step, and the purpose is to observe it. And with respect to energy scales, this is what I'm showing here in this slide. I think that this gives an idea of the reach. Another thing that determines the energy scale is the electron structure. And for instance, this is a xenon target. For electron recoils, we can achieve like around 1 GeV threshold here. So this is for a 2 GeV dark matter particle. We are unable to observe a nuclear recoil. This is way below. This is a nuclear recoil by an elastic scattering. But by a Migdal effect, we have this tail that goes above the threshold. So we will be able to see if there are GeV a bit low.
So what are in this plot the n equal 3, n equal 4, n equal 5?
These are for the different the spectrum for the different electron layers.
Okay.
Yeah. So depending on what electron is ejected, you have one spectrum, one spectrum or the other. Then you would observe that the integrated, but this is split in different parts.
Okay, thank you.
Yeah.
Okay. So actually, I don't see any more hands, so I have also a question. So when you go to the sub-GeV energies, you enter the domain of these polymetric experiments.
Yeah.
So what's the upper hand? So why is this Migdal effect being exposed? So I see, for instance, that in your plot that CDMS, it continues to have a better sensitivity than Migdal. So why are you pushing? What is the main motivation to push this, other than that it's one more measurement that you can do with xenon?
Well,
So
CMS,
let me put in some other way. Do you think that you're going to be competitive with these other polymetric volumetric measurements?
If this volumetric, there are two parts here. Using volumetric experiments using nominal operation, we can, as you can see here, we can reach similar thresholds in terms of energy threshold. This result shown here, it's for S1 and S2. If you signal, so with a given energy threshold in xenon, if you use only S2 signal, you can reach even lower thresholds. So even lower than this crest, which is one of the most sensitive in terms of energy threshold. So in terms of threshold, you can be competitive with this. In terms of exposure and I mean the lower limit here, this is for lax. So now we expect to have more mass and less backgrounds. So we can still push this this course down and be competitive with volumetric results in terms of rates. So I don't know whether, I think it's a bit early to say whether we will be better or not, but definitely competitive in both ways, in going to lower masses and going to lower rates. CDMS will have, I think it's complementary because it will explore this part here. But this region here can still be below 0.5 GeV, can still be explored with Migdal effect in xenon detectors. And again, you can also have Migdal effect in volumetric experiments, but because the mass is lower, it's much lower than these xenon experiments, the curve will not be as low as these ones. So there are several factors there, and it's it's going to be competitive, and I think it's early to say what is going to dominate here.
Okay, thank you for.
And again, the first step is to confirm the Migdal effect.
Of course, yes. Okay, so any more questions?
I have a question. I raised my hand twice. Probably it was the wrong hand. So my question is again about Migdal effect, and now it's about observational Migdal effect in that experiment that you are planning to do. So if you could come to slide 38, I think it's a signal. Yeah, it is a signal which you expect to observe. So first of all, I don't understand what is recoiling nucleus. It's probably ionized atom, and not the nucleus. How do you see the naked nucleus? So what happens with the other electrons?
Well, I think this is just an abuse of terminology. We call nucleus, but it's as you say, the atom.
Ionized atom. Okay. So then I think it would be more convincing if you show also the image of the normal ionization event. I mean, normal. Okay. What we usually think is normal. Not non-Migdal, let's say non-Migdal. So in my view, you can easily imagine a WIMP particle colliding with an atom and producing a recoiling atom, not necessarily ionized. And this recoiling atom then will sooner or later produce electrons and ions on its path. So what would be the difference? I would say that the signal would be exactly the same.
So that would be a delta electron, say, for example?
No, not necessarily delta. Just electron, which comes out from the atom in the ionization act by collision.
But they would be lower energy, right?
Not necessarily. I mean, how do you imagine the propagation of a positive ion, xenon ion in liquid xenon? So it mostly goes as a neutral atom, from time to time losing electron or exchanging electron with other. So it's mostly neutral, but from time to time it appears as a positive ion. So at that point, there will be electron.
Yeah, I see your point. I don't think we have calculated that, but we can, of course, we can include that.
Might be that what you're plotting is not electrons, but X-rays from the transition. So you imagine that you ionize the Migdal, for the Migdal effect, you ionize the level 5 or level 3, let's say, n equal to 3, what was in your plot. And then there will be transition in that ionized atom, and there will be X-rays.
Yeah, in this case, because the density is so low, the X-ray would travel a bit, and you would see some displacement in this case. So that would not be a background because of this displacement. You would see an electron but displaced. So in this case, we are confident that we can reject that,
Okay.
and because of the low density of the mass.
So the main difference, what I see between Migdal and non-Migdal, then non-Migdal is ionization of outer electrons, and the Migdal can affect the inner electrons, and then you expect transitions from the upper states. Okay, thank you.
Yeah, thank you for the feedback. Yeah.
Okay, great. So we are already a little bit over time, so I think we have to conclude here, but Elias is at LEAP, so if you have questions, please contact him. Thank you very much, Elias, for this seminar. Thank you all for being here, and bye everyone. Stay safe.
Bye.